So we're now in our next video about binomial theorem, and in this video I'm going to talk about clearly the binomial theorem. I think I mistitled the the video before. I put there the binomial theorem, but actually we didn't touch any binomial theorem there, only the coefficients, Pascal's identity, the triangle, and such. Well, this will be our last part of our Module 1, Fundamental Properties and Preliminary Considerations, back in our number theory major subject. So now, this time, I'm going to give you a proof of the binomial theorem itself. So let's restate that again, the binomial theorem. So we will let x and y to be part of our real numbers. And we also let n to be part of our non-negative integers, okay, or our whole numbers, shall we say. So if this exists, then we say that the quantity x plus y all raised to n is equal to the summation of n choose r running from 0 to n, times x, or rather of, not times, of n raised to n minus r, y raised to r. Okay, so that's clearly our binomial theorem statement. Again, if we have x and y to be real and to be non-negative integers, so we have if we have the binomial x plus y all raised to n, it's equal to the sum of all of this, n choose r, x raised to n minus r, y raised to r running from 0 to n. So we're going to prove this by induction. Okay, and then we're going to give a recall of the Pascal's identity if you haven't recalled that. So we're going to give a recall of that in a while, but say we'll give a proof of this, and we're going to prove this by weak induction, or simply by induction, shall we say, by ordinary induction. Okay, so let's have our basis step. Let's see if it holds. So for our basis step, some call it the basic step. Either way, okay. So when we say when n, we will let n equals 0. So since we started with 0 because our n is the whole numbers, and we know that whole number starts with 0, so non-negative integers. So when n starts with 0, so we have our left hand side, so we'll have the left hand side be, therefore our left hand side shall we write is equal to x plus y raised to 0, and we know any number raised to 0 is equal to 1. Okay, for all x and y in the real numbers raised to 0, those will be 1. And for our right hand side, shall I write it here? For our right hand side, so we have it's equal to the, this is the left right hand side, by the way, summation of since our n is 0, so shall we have our r here above? Okay, so we have our r to be our highest value, so 0 is here. So r chooses 0. R runs from 0 to this 0. Okay, since we have our first 0 here, we have x raised to 0 minus r, y raised to r. So this will be just equal to, so since r is until 0, so we have this all by 0, so it becomes x raised to 0, y raised to 0, and then this is equal to 1, and then we can see that clearly our left hand side and right hand side are equal. If you want, we can put that in a statement. So clearly we have our left hand side is equal to our right hand side, and we can say that the basis step holds. The basis step holds. Okay, so that's for the basis step. We have just proven the statement for the first theorem for the n sub 0. Okay, let's go to our induction step where this will be a bit of a well, it's interesting to look at the proof of this binomial theorem in the induction step. So shall we write here the induction step? Okay. Okay, so we assume in this step, we assume for the p of k is true at some k. For some k greater than or equal to 0, since 0 is our first element. So this will be our induction hypothesis. X plus y raised to k is equal to summation of k choose r, r running from 0 to k, of x raised to k minus r, y raised to r. Okay, so in some books they simply say it that you will let, if I will just put it here, you will let n equals k. In some books they made that simpler. So if you're going to notice in our formula before, actually in this right hand side, also in this left hand side, all the n's became just a k simply. Okay, so then we will try if we're assuming that this is true for p sub k, so therefore this must be also true by our condition number 2 in the weak induction. Then we can say that x plus y, sorry, x plus y raised to k plus 1, the next value after the k here, x plus 1 is equal to, it should be like this, summation of k plus 1 choose r, r running from 0 to k plus 1. So if I think you notice it already that we have just moved, okay, the k from the k here, it became k plus 1. The k here just became k plus 1 because we just moved one integer up, or the next consecutive integer after the k. So what we'll have here is it's going to be x raised to k plus 1 minus r. So if you want to make it clear, I'll put it in a parenthesis. This k here became k plus 1 times y raised to r. So this is our induction hypothesis. We are hypothesizing that this is true. So if this is true, therefore the induction holds, the induction theorem is being followed, and then therefore the binomial theorem is true. Okay, so let's start. So we're saying that this is um, true. So shall we say, let's try to um, what do you call this? We will try to manipulate this left hand side. K plus 1. This is said to be equal to x plus k, x plus y rather, x plus y raised to k times x plus y. What happened here? We just followed the law of product in the exponent. So imagine there's a 1 here. So if the bases are the same, so we simply add the exponents, right? So this k plus 1 can be written as this. Okay, now this is what we're going to do. I think I need to move the next step. So let me copy that again in the next slide. X plus y raised to k plus 1 equals x plus y raised to k times x plus y, simply raised to 1. So we say that x plus y is equal to, from our first statement, we know that x plus y raised to k is equal to this, right? So we need to copy the whole of it because they're equal. So since they're equal, we need to copy that. So have is, this is going to become the summation of k choose r rather, k choose r, okay, r running from 0 to k, x raised to k minus r times y raised to r, and multiply that by this binomial x plus y. Okay, next thing that we're going to do is actually we're going to distribute, try to imagine distributing this whole term here to this term x, to this term y. Oops, overshoot. Shooted. Okay, let me fix that again. This term y. So if that happens, what will we do? So we simply have an additional x term here, an additional y term in this part. So if you want to strictly put that, so what we have is x k choose r, x raised to k minus r, y raised to r, r running from 0 to k, and then plus y summation of k choose r, x raised to k minus r, y raised to r, r running from 0 to k. Okay, so what will be the next thing to do? Actually, we can put this literal, what do you call that? An absolute, rather, absolute coefficient. Okay, a literal coefficient here, and then we're going to put it as one of the factors here. So imagine if we're going to extract this summation notation, what we'll have is a bunch of terms, right? A bunch of terms. And in all those bunch of terms, we're going to multiply all those bunch of terms by x, 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 by x, by x. So why don't we just, put x inside the formula itself? So since we're going to multiply it, by the way, by all the terms here, likewise the y here. So if we're going to put that inside our factor, it's going to be like there's something x here. This x, since they're like terms, there's going to be some x that will be inserted in this factor here. So if it will be inserted, it will somehow look like this. Summation of k choose r, x raised to k minus r, times another x, times another, times y, okay, r running from 0 to k, okay, plus the summation of k choose r, x raised to k minus r, y raised to r, y, okay, this time it's y, where r is running from 0 to k. Okay, now imagine this. We're going to follow the concept of this thing here in this variables here. So imagine there's a 1 here, there's a 1 and there's a 1, and if that happens, we're going to follow again the law of product in exponents. If the bases are the same, we add the exponents. So we simply, if we simply put, actually we're going to simply put a plus 1 here. Likewise, just need to put a plus 1 here. Okay, I hope that is clear. Okay, so if that is kind of like a surprise to you guys, I'm going to undo that. Okay, and redo again. This has a 1, this has a 1 there, and then since this is a 1, instead of writing the x itself, we can just, oops, what happened? We can just put a plus 1 and put a plus 1 here. Okay, now that's our seconds. That's our, how many is that? Third line. That's our third line after this part. Now, the next line actually is a tricky one. Okay, it's a tricky part of the proof, and I'm going to show it to you now. So I'm not going to copy the previous line. It's going to be quite um, full if I'm going to write it again. So try to look at this part. What we're going to do in this first part here is we're going to take out the k equals, or rather the r equals 0, zeroth term. And here we're going to take out the r, sorry, r equals kth term. Okay, and then get it as a factor. Okay, now if we happen to do that, what will happen is, again, we're going to take out the r equals 0 term there. So we're going to take it out as a factor. So if that happens, what we will get is k choose 0, since we got the r equals 0, x raised to k plus 1, and then y raised to 0, which is just 1. But if you want, we'll just copy that. Plus, since we have taken out the 0, what will be left in our summation notation is k choose r times x raised to k plus 1 minus r y raised to r running from 1 only because we have taken the 0th term, r running from 1 to k. So we're starting with 1 now instead of 0. Okay, so that's pretty much our next step, and then that's only our first term. Okay, that's only our first term. In our second term, again, we're going to get the k equals, or rather r equals k term. So if we're going to follow that, what will happen, if I can put it down here, we're going to get the k, choose k, since r equals kth term. X is raised to y, okay, or rather x is raised to k, since r equals k minus k, okay, k minus k y raised to r plus 1. Okay, let me check that again. So we have this r here will become k, this r here will also become k rather. So let me change that. Should have become k. Okay, so that's just the term that we have taken out, and then this is going to be plus the summation notation that we have written. So what we have is, it's going to be k choose r minus 1, or rather only r, k choose r, x raised to k minus r, y raised to r plus 1. Okay, where r now runs from 0 up until k minus 1. K minus 1, because we have taken the kth term, since r equals k in this given, so we have taken the kth term, so therefore we end with k minus 1 instead of k, because the last term has been taken out. Okay, next up, I'm going to give you some reason why we did that in a while. Okay, after that what we're going to do is to actually we're just going to make this a little bit interesting now. So imagine this k choose 0, any number with this kind of notation, I mean any k that we do, any number will still become 1 because our r term is 0, and by definition that will be equal to 1. So why not? Just why not? Why don't we just change the k? Instead, we're going to write k plus 1. Choose 0. Anyways, it's still going to be 1, so they're equal. So there's no reason we cannot do that. And then we have x raised to k plus 1 it's okay not to write this anymore because that becomes 0, plus what we have is the summation of k choose r x raised to k plus 1 minus r. Anyways, I have made it k plus 1 minus r instead of k minus r plus 1 by commutativity. Okay, I hope you got it why it became there. R running from 1 to k. Okay, and then we're going to write this. This k on it, k choose k is still also 1 by definition. So I mean, why not? Why not we write it as k plus 1 choose k plus 1? I mean, they're still equal, right? It's still algebraically legal, right? This becomes k minus k. So essentially, for any k, for all k, x those will become x raised to 0. So it's still equal to 1. So don't write that. Y times y plus k plus 1. Okay, and then we're going to copy this summation. And what we're going to do in this step is to actually try to change, or we will kind of adjust the terms here in this term in such a way that it will end in k instead of k minus 1 because we lack 1k here. And if we are going to do that, actually everything else in here is going to adjust also. So what I'm telling you is like this. I hope it fits. The summation of k, since we will end now in k, this will be our summation notation now. Since we will move by 1, the r will also adjust by 1, right? Because we have moved all terms. We have moved by 1 step. Okay, so this becomes k choose r minus 1. Also one of the reason why we adjusted. Okay, so we need to change this r. We adjust 2 times. I don't know if I can fit this. X. This becomes k minus r, but we will try to adjust that to become k plus 1. Sorry, k plus 1. I think I cannot fit it. Let me move this down below. Okay, plus. Let's put it here. Summation of k choose r minus 1. Again, we have tried to adjust. Sorry. R equals 1. And then x raised to k plus 1 minus r. So actually, if you want, we'll put that in a parenthesis so that it will be clear. Sorry. Okay, so from k plus r to become k plus 1 minus r. So we have just adjusted in the k, and then it becomes y. Instead of r plus 1, we deduct it by 1. This will simply become r. Okay, and that's it. As you can see, all the k's from this term here, we have added 1 to all of the k, so this becomes k, except this first term here. This k, we have added 1 there. Okay, and all the r's we have minus by 1, so we have minus 1 here, and then we have minus 1 in this y, so that becomes just r. Okay, so after that, as you can see here, this second term in our expression here and this last term are now essentially the same, except this part, except the part of the binomial coefficients. They're not the same. So why not we just put them beside each other? Okay, we'll see what we can do there then from there. Okay, and then I'll copy the rest. Okay, so this will be equal to that's k plus 1 choose 0. This is essentially 1 times x raised to k plus 1. Then we'll put I'll put first the summation k plus 1 choose k plus 1, so that it'll be beside each other. Y raised to k plus 1 plus, I'll put them all down so that it'll be a single line. Summation of k choose r x raised to k plus 1 minus r y raised to r running from 1 to k plus the summation of k choose r plus 1, r minus 1 rather, x raised to k plus 1, sorry, minus r, y raised to r for all r running from 1 to k. Now what we will do here is we're going to by one of the summation theorem by the summation by the product summation notation rather, by one of the summation notation laws, that we can combine them, provided they have the same summation notations law here. Okay, we can combine them, and notice the only difference is they have the same parts here, as you can see. The only thing that is different are the binomial coefficients, so we're going to write it like this. I'll try to fit it right now. We have k plus 1, choose 0, x raised to k plus 1 plus k plus 1, choose k plus 1, y raised to k plus 1 plus the summation of from all for all r running from 1 to k. So what we can do is we're going to put it like this: k choose r plus, since it's a plus sign here, plus k choose r minus 1 times, or rather, it's still part of the summation notation, k plus 1 minus r, sorry, minus r y raised to r. Okay, so that's it. Now what we're going to do here, notice this part here. Actually, we can try to recall one very important theorem, or shall we say identity. In our previous video, we called that the Pascal's identity. So we will try to recall the Pascal's identity. Which I'm going to write it here. Which states that n choose k is equal to n minus 1 choose k plus n minus 1 choose r minus 1. Okay, so that's pretty much our Pascal's identity. So we're going to look at this part now of how we can use the Pascal's identity here. Here. Okay, so just notice that we have n. Okay, notice here we have both k's the same numerators. Okay, it follows this formula, same numerators. And then notice the r, the other addend is r minus 1, so this is k. The other addends is, oops, sorry, I have written this wrongly. This should be not, no, this should be not r, this should be k. My bad, k minus 1. Oops. Okay, so again, same essence, wrong variable. R here and then r minus 1. We have k here, k minus 1. So we can apply the Pascal's identity by making this term a single term, which is going to be, since this is all our n minus 1 terms, so this becomes k plus 1. Choose r. Okay, and we're going to use that in our next line. Sorry, we have a lot of lines here. It's a pretty long proof. Okay, I hope you can bear with me. K plus 1 choose 0, x raised to k plus 1, sorry, plus 1, and then we have plus k plus 1, k plus 1, choose k plus 1 rather, y raised to k plus 1, and then this is our new term, summation of by the Pascal's identity, so we have k plus 1 r Okay, choose R. X raised to k plus 1 minus R. Y raised to R for all R running from 1 to k. Now, this is going to be one of the last lines of our proof, I promise. What we're going to do now is to integrate these parts. Notice that what we have here, we'll just try to observe that our last line here, our upper bound here is k. Okay, it's k. So actually, we can adjust the upper bound by adding up an r equals k plus 1. So in essence, we are adding this up to our upper limit, and then this one, we're adding this. This is our r, right? So r equals 0. So we'll also adjust in the lower bound to make it 0. Okay. So by doing that, well, that's the essence. You may want to add this yourselves, but that's the essence of the line, so that we can save lines. So what we will do actually is going to end up like this. So the summation of k plus 1, choose r, x raised to k plus 1 minus r, y raised to r we adjusted, r running from 0 up until k plus 1. And this seems familiar. Let's try to have a throwback. It's a pretty long proof. Let's have a throwback. And I think this pretty much looks like this. Okay, let's look at it again. Let's read this. Summation of k plus 1, choose r, x raised to k plus 1 minus r, y raised to r running from 0 to x plus 1. And this is our last line, which is exactly the same from that induction hypothesis of ours. Okay, so if you want, we can write something like, in a moment, we can write something like this is equal to your left hand side. So, or rather, this is equal to your right hand side since we've manipulated the left hand side. Okay, either way, the left hand side is equal to the right hand side, as we can see, pretty much. So let's write our statements after this slide. Thus, therefore, by weak induction, or simply by induction, ordinary induction, the formula is true, the theorem is true. Okay, the formula, the binomial theorem formula is true for all integers greater than or equal to 0. This is n for all integers. Okay, and that's pretty much the end of our proof for this binomial theorem. Okay, for our binomial theorem. And yeah, that's a pretty long proof to start with. Let's have a throwback of it, a little bit of recap. So we started here in our induction hypothesis. Let me delete this. So this is our induction hypothesis that this left-hand side is equal to the right-hand side. So we manipulated the left-hand side clearly, and this becomes this. We use the value of this equation to make it, to change this value. So in the next line, it became like this one. Okay, and then what we did is distribute this long term to the x and the y. We have this, and then we have this pretty much interesting step here. Oh, I told you to give you an example to explain. So the reason behind this is that this r starts with 0 and then it ends with k, while the other one, okay, ends with r equals 1, and then it will be ending in k plus 1. Okay, it fits. Now what we did here is that we pretty much took these parts here, and then they're pretty much the same. Okay, and then we took care of the say the tail parts. No, not really an outlier. That's technical. So these parts we took care of that. That's why we took them out, so that we can make them a single term. Actually, we can make them a single term. So that's why to make them a single term, we have did some manipulation here, and then yeah, actually we made them with them in a single term in this part. That's why we took out this part. This is the r equals 0. This is the r equals k plus 1. So we made them a single term by the power of the Pascal's identity, and then pretty much mm, put again the terms back. When putting the terms back, we end up in this single term, and then voila, it turns out that it's equal to the right hand side. And yeah, pretty much that's the end of the theorem. And then we have proven that the binomial theorem holds, that indeed um, that indeed for all x and y in the real numbers, and some n, and all the n in the non-negative integers, x plus y quantity raised to n is equal to the summation of n choose r, x raised to n minus r, y raised to r running from 0 to n, and then they're equal. Okay, so I think I need to add more videos. I thought this would be the last one, but it's pretty long. It's pretty long proof. So I'm going to add another video. There's a very important corollary after this theorem. It's quite short, but I promise that after this video I'm going to give more examples, or one or two examples that you will apply the binomial theorem in it. Okay, so that's it for this video. Thank you very much for watching, and see you in the next. Okay, don't forget to like and subscribe, by the way. Okay, bye bye.